These are examples and practice problems for section 10.1, radicals in the Pythagorean Theorem. Example 1. Simplify and approximate the square root of 20. Simplifying a radical or square root and approximating one are two different things. I'm going to start with approximation because this is probably what you're most used to. In Algebra 1 last year, you learned how to simplify these. But before we do that, let's approximate first. To approximate a square root, you simply take that number and using either a calculator or a chart that has square root values in it, take the square root of that number and you'll see that you get a number that is has many places after the decimal point. Now this continues on and on without a pattern. Of course, this is called an irrational number because of this, and we have to agree upon what place value to round to. A lot of people round to the whole, the ones place, or the whole unit, or the tenths, or the hundredths, sometimes even the thousandths place. We're going to round to the tenth place. So remember when rounding, we go to the place immediately to the right of the place you're rounding to, which in this case would be the hundredths. And if this number is 0 through 4, then this number stays the same and you drop all these digits and we would get 4.4. But if this number is 5 through 9, this next digit, and it is 7, it pushes this up one more to 5 and you drop all the rest of the digits. So we get the square root of 20 is approximately equal to 4 5/10, or 4.5. This is the symbol for is approximately equal to. Now when simplifying the square root of 20, you take the radicand, which is the 20, whatever's underneath the square root, and you think about all of that number's factors. There's 1 times 20, 2 times 10, and 4 times 5. We're only interested in the pair of factors that has one perfect square in it. Now remember, perfect squares are numbers, rational numbers, that when you take the square root of them, you get another rational number. For instance, the square root of 16 is 4. We took the square root of a rational number, we get a rational number. So 16 is a perfect square. Not 4 necessarily, but 16 is. Another one would be something like this. 9 25ths, and the square root of 9 25ths. The square root of 9 is 3. The square root of 25 is 5. Those are both rational numbers. And so 9 25ths is also a perfect square. Now we're going to mainly be interested in the whole number perfect squares, like 16. So refer to the list on your notes of the partial list of perfect squares 1 through 20. So notice in this list, the only pair that we would be interested in then to have a perfect square in for one of our factors is 4 times 5, because of 2, 10, and 5 are not perfect squares, and 4 is. So we're going to use 4 times 5. Now why not use 1 times 20? 1's a perfect square. The reason why we're not interested in 1 times the number that we're using is because it's not going to affect any kind of change. We're still going to have 20 underneath the square root. So we never use 1 in the number itself. So we're going to use 4 times 5 because 4 is a perfect square. We rewrite this as the square root of 4 times 5. Now once you've done this, the next step will be to use Algebra 1. One of the rules you learned last year, when you have the square root of a product, it's exactly the same thing as the product of the two square roots. So the square root of 4 times 5 can be written as the square root of 4 times the square root of 5. It's that simple. Once you've done this, you take the square root of the perfect square, which is simple enough. The square root of 4 is 2. No more square root on it. Notice that. Times, and then you come over here and you try to do the same thing you did before. Well, 5 has, the only factors of 5 are 1 and 5, and since we said we're not interested in 1 in the number, There are no other factors for 5 that are perfect squares. Therefore, this stays underneath the square root. And then we don't need the multiplication symbol, so we get 2 times the square root of 5. So 2 root 5, or 2 times the square root of 5, is the simplification of the square root of 20. Again, the approximation of the square root of 20 rounded to the 10th place is 4.5. So these are your two answers. Now, try practice 1 on your own. Pause the video and try practice 1. Simplify and approximate the square root of 18. Okay, here's the simplification of the square root of 18. The square root of 18 has several factors to it. The factors we're interested in are 9 times 2. So the square root of 9 times 2, because 9 is a perfect square. This gives us the square root of 9 times the square root of 2. And this gives us the square root of 9 is 3 times the square root of 2. And so 3 times the square root of 2 is the simplification of the square root of 18. Now for the approximation for the square root of 18, putting in the square root of 18 in your calculator, we get 4.242640687 and so on. We want to round to the nearest tenths place like we did before. So the square root of 18 approximated to the nearest tenths would be 4.2, or 4 2/10. Example 2. Many times we need to multiply or divide square roots or radicals. So in example 2 it says multiply and simplify. Here we have the square root of 5 times the square root of 8. 5 is not a perfect square. 8 is not a perfect square. But before we try to multiply these together or try to simplify these, let's go ahead and multiply them together first. So this gives us, using the rule that we talked about on the previous example, we can put these two together, go in the other direction. The square root of 8 times the square root of 5 is the square root of 5 times 8, all underneath the radical symbol. And then that gives us the square root of 40. Once you get one number into the square root, then you start looking for factors for 40 that are perfect squares. So 40, there's 40 times 1, which we're not interested in. 2 times 20. 2 and 20 are not perfect squares. Then there's 4 times 10 and 5 times 8. 5 and 8, of course, weren't it, but 4 times 10, 4 is a perfect square. So we factor this 40 into 4 times 10, so we have the square root of 40 is equal to the square root of 4 times the square root of 10. Now we split these up once again using the law that we mentioned before, and we have the square root of 4 times the square root of 10. The square root of 4 is 2. It's a perfect square, 4 is. And the square root of 10 doesn't have any factors but 2 and 5. 2 and 5 are neither one of them are perfect squares. So the square root of 10 does not simplify. So we have the square root of 10. 2 times the square root of 10 is the same as the square root of 5 times the square root of 8. Now you try practice 2 by pausing the video and then checking it after you finished. Practice 2, multiply and simplify the square root of 3 times the square root of 8. The square root of 3 times the square root of 8 is the same as saying the square root of 3 times 8. And the square root of 3 times 8 is the same as saying the square root of 24. Looking for factors of 24 that will give us a perfect square factor, we would choose 4 times 6. So the square root of 4 times 6. Split those up. The square root of 4 times the square root of 6. The square root of 4 is 2. That's 4 is a perfect square. 6 is not a perfect square, and 6 doesn't have any perfect square factors. 2 and 3 are neither one of them are perfect squares. So the square root of 6 has to remain underneath the radical, and so the answer to this, simplified, is 2 times the square root of 6. Example 3. The diagonal of the flat screen TV shown is 36 inches. So in a television, the screen's diagonal is always measured across from corner to corner. It could have been this one also, but they're using this one. So this is 36 inches. And by the way, when you buy a television and they advertise it as a 36-inch television, they are referring to the diagonal, not the width and not the length. They're referring to the diagonal. So this would be a 36-inch television. Write an expression that can be used to find the height of the TV screen. The height, this way. So I'm going to let this be the height, h. And then it says find the exact height, then find the approximated height to the nearest inch. This time we're rounding to the ones place. Anytime a problem tells you to round to the nearest inch, the nearest foot, the nearest mile, the nearest square foot, the nearest whatever named unit, they're always referring to the ones place. So several answers we're looking for on this problem. To start off with, notice we have a right triangle formed with the diagonal of the television. We assume this is a right angle here between the bottom and side of the television. Our length in this right triangle is 30 inches. Our diagonal or hypotenuse is 36 inches. And our height is h inches. And they want us to write an expression that can be used to find the height. So we're going to use by Pythagorean Theorem. Take the hypotenuse, which is 36, square it, and that's going to equal the sum of the squares of the two legs. So h squared plus this length, 30 squared. This is an expression that can be used to find the length of that height. So there's our first answer. Then we take this and we solve for h. So we have 36 squared. 36 times itself is 1,296 equals h squared plus 30 squared. Watch this. 3 squared is 9. And because it's squared, we have 1 0 creates 2 zeros, so 900. 30 squared is 900. Then we solve this equation, solving for h. We have to solve for h squared first, so we subtract 900 from both sides. When we subtract 900 from both sides, over on the left we get 396. Over on the right we have h squared. Now we have not solved for h yet. We have to get rid of the square, or the second power here. The inverse operation of squaring a number is to take the square root. So to get rid of this square, we can take the square root. The square root of h squared gives us just h. But in an equation, whatever you do to one side, you must do the exact same thing to the other. So we come over here and we take the square root of 396. Now they wanted us to find the exact height, so we're going to have to deal with the finding factors of 396 here. So the square root of, one way you can do this, as I've discussed before, when you're looking for a factor of a fairly large number to a very large number, you can use your graphing calculator, going to the y equal key, clearing out anything that's in there, put in the number you're factoring, 396, and then divide by the x key right here, xt theta n, the x key, and then hit second function, and then right up here, table, in the upper right hand corner, table. This will give you a list of all the factors. We're only interested in the whole number factors. It's always a good idea to start lower in value. So I'm going to go down a little bit further, down to 1. We have 1 times 396, 2 times 198. We're looking for a perfect square in one of these lists. So as we go through, 1 and 396, we don't care about those two. 2 and 198. 198 is not a perfect square. Then we go over to, we keep going down until we hit, and there's 4 and 99. 99 and 4. 4 is a perfect square. See if we can find another perfect square besides 4, though. Maybe there's a larger one. Let's keep going. We have 9 and 44. 9's a perfect square. what about, since 9 and 4 are both perfect squares, 9 times 4 is 36. Let's see if 36 is a perfect square. Go to 36. Yes, 36 times 11. 36 is a perfect square number. So let's use 36 times 11. 36 times 11. Now, let me just make a note here. If we had used 4 times 99, we could still work this problem. You'd take the square root of 4 and you'd still have the 99 left, and then you would have to just repeat the process of factoring and taking the square root. I used the highest perfect square here so that it won't take us quite as long. Once we've done that, we split these up. We have the square root of 36 times the square root of 11 equals h. The square root of 36, 36 being a perfect square, is 6 times the square root of 11 equals h. 11 is not a perfect square, and 11 doesn't have any perfect square factors, so the square root of 11 must remain this way. So we found the exact height. It's 6 times the square root of 11 inches. Now, when we find the approximation, most students find it simpler and easier just to go back up to the original radicand that we had, 396, and just simply take the square root of that and approximate. By the way, to get out of the screen, you hit, you go up to graph, hit graph, and then clear once the graph has gone through its cycle. So I'm going to put in the square root of 396. And that gives me approximately 19.89974874 and so forth. They wanted us to round to the nearest inch, so that would be the ones place. So the height, the approximate height of this television would be 20 inches. Here's the expression we used by the Pythagorean Theorem. Here's the exact height of this television, 6 times the square root of 11 inches. And here's the approximate height, rounded to the nearest inch, 20 inches. Example 4. The square ceramic tile shown must be cut along one of its diagonals. What will the length of the cut be? Find the exact answer. Okay, so we have this tile. It says it's a square ceramic tile, and the word square is very important here because it tells us one of our dimensions that's not written on our diagram here. Since this is 14 inches and this is a square, all the sides must be 14 inches. So that means the height also is 14. I'm going to mark that. I'm going to draw one of the two diagonals in this square. I can choose either one. Remember, a diagonal goes from one vertex to another vertex in the figure, in the polygon, without tracing one of the sides. So I'm going to use this one right here. I'm going to use a dashed line. This is where they're going to cut it. And voila, we just created a right triangle right here, where these two sides are the legs, and this is the hypotenuse of the diagonal is. Well, they want us to find the length of that cut, so I'm going to call this length D for diagonal. They want us to find the exact answer, so be prepared to use your simplification skill here. We have this right triangle, and so by the Pythagorean Theorem, we have the hypotenuse, which is D squared, equals the sum of the squares of the two legs. Well, the two legs are the same. So we have 14 squared plus 14 squared. And so here's our expression that we use. Starting to solve for D, we need to solve for D squared first. So D squared is equal to, using the order of operations here, we need to square before we can add. 14 squared is 196. So 196 plus 196, or 196 times 2. That gives us 392. So d squared is 392. Now instead of taking our calculator and just taking the square root of that, it's asking us to find the exact answer, not the approximation. So we need to next get rid of the square on the d, which means we need to take the square root to get rid of it. That means we need to do the same thing over here. We need to find a perfect square factor for 392. If you use a little bit of math sense here, you can figure this out a lot quicker than just taking your calculator and finding factors. Notice that this came from the adding of two 196 numbers. In other words, 2 times one factor, 196. So 196 plus 196 gives us 392. That means we can, instead of splitting it up into these two, we can split it up into 196 times 2. This is the same as 196 plus 196. And we already know 196 is a perfect square because we squared 14 to get it. So the square root of 196, let's go ahead and split them up, times the square root of 2. The square root of 196 is back to 14. So d is 14, 196 being a perfect square, times the square root of 2. And of course 2 is not a perfect square. So this is the exact answer of how long the diagonal for this tile, the square tile, is. It's 14 times the square root of 2 inches long. That's the exact amount.